Hi.
See the link to the data, the presumed data? Is that
Let's see. If you go, oh, the preparation, right? Sorry. Okay. Yeah. If you go to the preparation link.
I'm just gonna copy it. It just brings me back to the same page here.
Oh, it must be a broken link. Let me see what they've done. Ah, okay. Let me. I'm just going to switch screens here, and I'll show you. I'll give people a few more minutes, but while you're setting up, what you might want, you can, if you go to the site for this talk, you can get my slides from there, and you might want to open up my slides in one window so that if I'm not on the slide that you're looking at, you'll have those to go, you can go back and forth. I'm going to be switching back and forth between my slides and a window where I'm going to execute Python code and a window where I'm going to edit Python code. Now I'm using Emacs and then I'm just running Python from the command line. If you want to use a notebook, that should work fine. You can use whatever environment you want. But in general, I think if you can set yourself up so you've got my slides and a development environment of your favorite kind, we'll go back and forth a little bit. And I'm going to give people a couple more minutes to come in and get set up, and we'll start in about 3 minutes. All right, I think we've got everybody. We can get started. So if you are here for Bayesian statistics made simple, you are in the right place. I'm Alan Downey. I teach at Olin College. It's a small engineering college just outside of Boston. We started up about 10 years ago. Our mission is to fix engineering education. And part of that is that we get to do all kinds of crazy experiments. And one of my crazy experiments is teaching undergraduate statistics, Bayesian statistics, to undergraduates. And this tutorial is part of what came out of that. Again, you're going to want to have my slides up, and that's that link. So the plan for today, I'm going to start out with Bayes' theorem. And this is, I'm going to do a straightforward derivation of where Bayes' theorem comes from and explain what it means and how it's used. We'll use that to build up Bayesian statistics, and from there, Bayesian inference. Part of the approach that I'm taking is computational. So we're going to do a little bit of math at the beginning to derive Bayes' theorem, and then everything after that is computational. My theory is that if you approach this stuff computationally, a lot of topics that are hard mathematically become easy. So for example, Bayesian statistics analytically involves a lot of integrals. If you replace the continuous mathematics with discrete mathematics, all of those integrals just become summations. And in code, they become simple for loops. So I think everything can be pretty straightforward. And then we're going to have a bunch of example problems to work on. I'm going to try to talk for about 10 or 15 minutes, and then you guys will have an exercise to do. I'll come around and help you out. So that's what the structure should be. At the end of the talk, I think we're done at 4:40, if I remember right. You should be able to take the kinds of problems that we do during the tutorial and solve similar problems if they come up in related work. I'm also going to give you some reading so that you can go off and learn some more things on your own. And that reading is going to include Think Bayes. So this is my book on this topic. The PyCon tutorial series is partly responsible for this book. I taught this tutorial the last 2 years while I was working on this book, and then just published it a few months ago. It's published by O'Reilly. There's also a free version of it that's available at thinkbayes.com. So if you want to have a hard copy, you can. If you want to read the PDF, you can do that. All right, let's get into it. A little bit of notation. I'm going to write P of A for the probability that A occurs. You can think of A as an event that might happen or not. You could think of it as a hypothesis that might be true or not. So probability of A. Probability of A bar B is the conditional probability. That's the probability that A is true given that B is true. Okay? And then, so those are just definitions. That's just notation. The thing at the bottom is the law of conjunction that says that the probability that both A and B are true, well, it's the probability that A is true, P of A, times the conditional probability of B given that A is true. I'm not going to prove that. I'm going to assert that that is a law of probability. I'm going to use that to derive Bayes' theorem. So first, just applying that the definition that I had on the previous slide, the probability of A and B should be equal to the probability of B and A. I can write it either way. And if I just take the right-hand side of those two equations and equate them, I get what I'm going to call equation number 2. And now this is the highest mathematics we're going to do today. I'm going to divide both sides by the probability of B. And the result is Bayes' theorem. Okay? So congratulations, we just proved Bayes' theorem. The reason I did that is partly just to show that this is just a fact of probability. This part is uncontroversial. If you've heard about Bayesian statistics, you've probably heard people going back and forth about frequentist statistics and Bayesian statistics. And Bayesian statistics, when it comes up, is often presented as this new thing that's really radical and controversial. And at least this part is not controversial at all. This is just a mathematical fact. A couple of ways to think about what Bayes' theorem is. Partly, it's a divide and conquer strategy for evaluating conditional probabilities. So if you want to find the thing on the left, the probability of A given B, one way to do that is to evaluate the 3 things on the right. And if it happens that the 3 things on the right are easier than the 1 thing on the left, then you've got an algorithm. And that comes up fairly often. In fact, an example we're going to do in a minute demonstrates that, where the thing on the left is not obvious, but the things on the right are. So it's a divide and conquer strategy. That's one way to think about Bayes' theorem. Another way to think about it, and this is the foundation of Bayesian statistics, is the diachronic interpretation of Bayes' theorem. Diachronic means through time. And the idea is that you have a hypothesis, and before you see any data, you have some belief about that hypothesis, or a probability for that hypothesis. So P of H is the probability of the hypothesis before you see the data. Someone comes along with some new data, D, and you're computing the conditional probability of H after you've seen the data. So that's the diachronic interpretation of Bayes' theorem. Here's the example. This is one of the classic cookie problems. This is an urn problem. If you've taken a probability class, you probably drew a lot of marbles from imaginary urns. This is the same thing, except it's cookies from bowls. 2 bowls of cookies. One of them is mostly vanilla, 30 vanilla, 10 chocolate. The other bowl is 50-50. You don't know which bowl is which. You choose one of the bowls at random. You draw a cookie from the bowl at random, and it turns out to be a vanilla cookie. And the question is, what's the probability that you drew that cookie from bowl number 1? Intuitively, we have a little bit of a feel that it was more likely to be bowl 1 than bowl 2 because there are more vanilla cookies in bowl 1 than bowl 2. What Bayes' theorem lets you do is make that quantitative. So we have some intuition. Now we're going to do it quantitatively. So again, we have a prior belief about whether it was bowl 1 or not, and we're going to use the data. In this case, the data is a vanilla cookie to update the prior belief and get the posterior belief. Here's what that's going to look like. The top line is just Bayes' theorem again. P of H is what you believe about the hypothesis before you see the data. I already used the word prior, but now I'm telling you what that means. That's the prior probability. P of D given H is the conditional likelihood of the data. What's the chance of seeing a vanilla cookie if the hypothesis is true? And the denominator is the total likelihood of the data. What's the probability of seeing a vanilla cookie under any circumstances, whether it's bowl 1 or bowl 2? We can plug in the numbers for that. So if I picked the bowls randomly with equal probability, then my prior is 50-50. I don't know whether it's bowl 1 or bowl 2. The conditional likelihood of the data is the probability of drawing a vanilla cookie from bowl 1. We know the composition of bowl 1. It's 3/4 vanilla cookies, so the conditional likelihood is 3/4. And then the one that takes a little bit of thought is the denominator, which is the total likelihood of the data. In this case, because I chose the bowls randomly and then chose a cookie at random from the bowl, it's the same as if I just dumped the 2 bowls into one big bowl and drew from that. So the total likelihood of the data is the probability of drawing a vanilla cookie from the total collection of cookies. And in this case, they are 5/8 vanilla, so that's my denominator. That clear? Any questions about what I've gone through so far? All right. And then having done the 3 pieces on the right-hand side, I just have to plug them in, do some arithmetic, and it comes out to 3/5. So the posterior probability of the hypothesis is about 60%. The prior was 50%, the posterior is 60. So consistent with our intuition, it went up a little bit. The vanilla cookie makes us think it's a little bit more likely to be bowl number 1. Good so far? All right. And that's what I just said. All right. So far we're doing this mathematically, just doing arithmetic, sort of on paper and pencil. I want to show you a computational framework for doing all this. The UML diagram there is an outline of where we're headed. I'm going to start out using a PMF, which is a probability mass function. A PMF is a map from all the possible outcomes. In this example, it was 2 possible hypotheses. But in general, a map from all of the possible outcomes to their probabilities. So you all are Python programmers. If you were representing a map from values to probabilities, what built-in Python data structure might you choose to represent that map? Dictionary would be a fine choice. And in fact, that's pretty much what a PMF is. So we're going to be working with a library today that I wrote that's useful for this stuff, but it's mostly just simple translations to basic Python stuff. In this case, the PMF object that we're working with has a dictionary that represents that mapping. Okay. So we're going to get into the coding piece of this. How many of you, I walked around a little bit at the beginning, so it sounds like a lot of you got this working. How many of you were able to get the install test working correctly? Okay. What I'm going to do, I'm going to pair you up to work together. And so if only one of you has a working environment, that's fine. You can do a little bit of pair programming. We'll do that in just a second. All right. So find somebody nearby. If you don't have a neighbor who has a working environment, we might shuffle people around a little bit. But again, if you can assemble yourselves into pairs and make sure you've got at least one working environment between the two of you, and then introduce yourselves to each other. This is one of the things that I hope for this tutorial, is that it's not just me up here talking, that you all get to know each other and work together and learn some stuff. And if you can't think of any topics of conversation, these are them. Are you going to be a group of 3? Great. And you guys, I know you have a working environment. I know you guys are all set. Excellent. Did you guys just join at the last minute? Have you had a chance to run the preparation?
Yes.
You have, okay. And you have a working environment? Okay, great.
Just running the install.
Yes. Yeah. Yeah, that just confirms that you've got matplotlib, you've got scipy, you've got everything you need. Let's see, and are you guys working together?
Maybe.
You are now.
I think I have all the stuff, but it's not working. It's like taking a really long time to render the script or something like that.
Oh, the first time you run it, it might take a long time because it's compiling a lot of the Python libraries? Maybe?
No, all this stuff should be installed.
Oh, okay.
When I tried to run a terminal, it basically hasn't gotten anywhere. But I ran it in the notebook and it generated a plot almost instantly.
Oh, okay. That could work. And are you, so but between the two of you, you're all set? You guys are all, you got an, okay. Have you guys got a working environment between the two of you? Excellent. How about you guys? You've got an environment working? All set?
We got at least one.
At least one. That's all you need. Whoops, sorry. All right. Have you got a working environment? Or at least one? Excellent. And are you 3? The 3 of you, good? And you're good? How about you guys? Is it going, it's working? Very good. That looks good. Good. All right. I will confess to that in just a minute. Okay, let's reconvene. So I appreciate that. I asked you guys to talk to each other, and you actually did, which is good. I can't get my students to do that. I'm curious now, who's got the earliest first computer in the room? My first was a PDP-7. Anybody top that? Maybe not. Okay. How about first programming language? QBasic? Mine was BASIC on the Commodore 64. And then 6502 assembly code. And longest time you've spent with a stupid bug? It has to be really stupid. It has to be the kind of thing where when you finally find it, it's just awful. Have you got a good one?
The JavaScript trailing comma. I've got a theory that everybody remembers the first time they came across that. Yeah.
And
I don't remember how long it took me, but I felt like an idiot after.
that's the worst because it was trying to help. The language was trying to be your friend.
It works fine at like Firefox.
Yeah. And do I remember, if I got it right, that was one of the ones where your program was technically incorrect, but it was trying to be helpful by interpreting it as if, by guessing what you meant.
It's not strict JavaScript to have a trailing comma, but Firefox
Yep.
and Chrome are just like, whatever. With IE that explodes.
Oh, yeah. Yep, that qualifies. Good one. Okay, good. All right, let's get some code running. So if you downloaded my code, simplest way would be to just clone it from GitHub. You should be able to CD into that directory and at least be able to import PMF from ThinkBase. So let me run that. I think I'm in the right directory. Yep. Fire up Python. Good. It works for me. And if that works, then try this. So this is going to be a probability mass function that represents a 6-sided die. And again, I'm going to go back and forth between my console and these slides. So when I leave the slide, you're going to want your own copy of the slides running. When you construct this PMF, initially you can set the probabilities to be whatever you want. I initialized them all to 1, but of course if you've got 6 values and they all have probability 1, then the total probability adds up to 6, and that doesn't make any sense. That can't be a real probability distribution. But it comes with a function called normalize. And all that does is to add up the total probability in the PMF and divide through by it. So you know when you've done that, that the probabilities will all add up to 1. And so if you print it again, you should see roughly 1/6. That's the floating point approximation of 1/6. Good so far? Is this working for people? Excellent. And the PMF class comes with a bunch of methods, including things like random, where you can draw a random number. And so every time you call that, it's the same as rolling a 6-sided die. And if you rolled it a whole bunch of times, you should see that the average outcome, or each one comes up with equal probability. Okay. So that's my library. One of the things that you probably think when you encounter this library for the first time is that it is not compliant with the PEP 8 style guide. In particular, I have a lot of functions and methods that all begin with capital letters. They're all in camel case. There's actually a good reason for that. I worked on a lot of this library when I was working at Google. Their style guide requires this style with capital letters and camel case function names. And then you kind of get used to it. And I kind of like it. So I'm going to stand up here and casually blaspheme by saying, I don't like PEP 8. I would rather have capital letters for my functions and methods. Oh, OK. All right, I won't tell. OK. So we've got this PMF object. We're now going to use this PMF object to do some of these Bayesian computations. And what this framework is going to look like is you're going to start out by using a PMF that maps from each hypothesis to its probability. You're going to use the likelihood of the data to update each hypothesis in the PMF. And then when you normalize the PMF, what you're really doing is dividing through by the total likelihood of the data, which is P of D, which is the denominator of Bayes' theorem. Okay? So all the pieces of Bayes' theorem are there. We're just going to see them now in their computational form. So we're going to create another PMF object. This one I'm just going to call PMF. And again, the first step is to make a map from each possible hypothesis to its prior probability. And I'm using strings here to represent the hypotheses. We're going to see examples soon where the hypothesis might be a number. The hypothesis could be any kind of Python object. It has to be hashable, but other than that, it can be any kind of Python object. So set this up. So PMF. In this case, I started with priors that were already normalized, so I didn't have to run normalize. Okay? So this PMF represents my prior belief about these two hypotheses. Now to do an update, I'm going to compute the conditional likelihood of the data under each hypothesis. So I want to know the probability of drawing a vanilla cookie from bowl 1, the probability of drawing a cookie from bowl 2. And again, that's straightforward. We know that that bowl 1 is 3/4 vanilla. We know that bowl 2 is 50%. And I'm going to use the mult method. What the mult method does is it finds the probability associated with bowl 1 and multiplies it by 0.75. Finds the probability associated with bowl 2 and multiplies it by 0.5. So this is the update. So when you take your prior and you multiply it by the likelihood of the data, that's a Bayesian update. If you print the PMF now, you will see that it's not normalized anymore. Okay? So those values, those probabilities are now relative, they are correct relative to each other, but they're not normalized. I need to divide through by the total likelihood of the data, and that's what normalize does. The return value from normalize is the total likelihood of the data. And that's the probability of D, or it's also called the normalizing constant, because it's the normalizing constant. And now if I print the posterior distribution, this is now a map from each of my hypotheses to the posterior probability. And we see again that the posterior probability of bowl 1 is 0.6, which is what we computed on paper a few minutes ago, so it checks out. This is what I did a minute ago. All right. Good so far? All right. If that is all making sense, then I have one more exercise for you. So suppose that I draw another cookie from the same bowl. I'm still not sure which bowl it is, but I am drawing from the same bowl, and suppose that that second cookie is a chocolate cookie. Okay? I want you all to do an update based on this new evidence. And let's assume that the bowls are really big, so it doesn't matter whether I replace the cookie or not. The probabilities are the same. So the bowl number 1 is still 3/4 vanilla. Bowl number 2 is still 50-50. I'm going to come around and look over your shoulders and see if this is making sense. Any questions? Do you feel like you know what to do? No? Okay.
Yeah, so we're trying to update it with
Mm-hmm.
we have whatever the PMF, and so what's the update we're trying to make?
So now you've seen a chocolate cookie. So you want to compute the likelihood of the data if it's bowl 1, and the likelihood of the data if it's bowl 2. Let me give you 2 hints if this isn't quite making sense yet. So the first one I mentioned on the slide is that we started with a prior that was 50-50 prior. We saw a vanilla cookie and we did one update, and now we've got a posterior that's 60-40. When the new piece of data comes in, that posterior, the 60-40, is now going to be the prior for the next update. So we're going to keep the same PMF, don't create a new PMF, and then what you do next is going to look a whole lot like this. So for this new cookie, again, you're going to do 2 mult invocations, except now you're going to compute the probability of chocolate from bowl 1 and the probability of chocolate from bowl 2. That makes sense? So it's going to be the same 2 lines of code with different values, and then normalize again. And that's what each update is going to look like. Is you take the prior, you multiply each hypothesis by the likelihood of the data, and then you renormalize. Yes? Good question. So the question is the likelihood of a chocolate cookie from bowl 1 0.25? Yes. And the likelihood of a chocolate cookie from bowl 2 is also 50-50. So I think we want to do something like this. Yep. Yes, I'm doing a lot of sneaky things today where I'm actually giving you the solutions to things. So if you're a little bit stumped, feel free to either look ahead to the next slide, or in a minute when we start looking at code, the same directory that you downloaded that has all the exercises also has the solutions. So don't feel like you have to suffer. Feel free to cheat. Cheating encouraged. All right. So let's just see what that looks like. We're going to do multiply bowl 1 by 25, multiply bowl 2 by 50%, renormalize, and print that distribution again. And you should see a result that looks like that. So now, having seen 2 cookies from this bowl, and having seen 1 vanilla and 1 chocolate, we've actually changed our mind, and now believe that it is more likely to be bowl 2. Okay? And you could keep doing this. As each new cookie comes out of the bowl, you could update your belief, and after you've drawn a large number of cookies, you'd probably be pretty confident about which bowl it was. Yeah, sure. Yes, it would change the numbers slightly if I did not put the cookies back. However, there's one important part of this. So that's a relatively minor thing. There's one other thing that you could have done wrong that would be a bigger wrong thing, which is you need to make all of your updates before you renormalize. If you update one of your hypotheses and then renormalize and then update another hypothesis and renormalize, that will not be the correct answer to a Bayesian update. All right. I think we are done with cookie problems. So far we've got Bayes' theorem, we've got the PMF class, and we've got this framework for doing Bayesian, not quite statistics yet. So far we're really just doing probability. We're not quite doing statistics, but we're getting there. The next step is going to be what's called the dice problem. So the framing of the problem is I've got a box of dice, I have a 4-sided die, 6-sided, 8, 12, and 20-sided die. I actually do have such a box. This is not a hypothetical question. Suppose I select a die from the box at random, roll the die, and I get a 6. What I'd like to know is which die was it? Now this is it's a toy problem. Obviously I would just look at the die. But this is going to be a model for the next problem that we're going to do that is a real problem. So let's again think about this intuitively a little bit. What's the probability that I rolled a 4-sided die and got a 6? Probably 0. So at this point I've ruled out the 4-sided die. What about the 6-sided die? Does it seem reasonable to believe that I would get a 6? Sure. 20-sided die, I could get a 6 out of a 20-sided die. So our intuition doesn't give us a strong feeling about which die it is. But here's what we can do. I'm now going to take that PMF object. We're going to take one more step. I'm going to define a new kind of thing called a suite. And what I mean is a suite of hypotheses, which is like a set of hypotheses. You can think of a suite as a map from each hypothesis to its probability. And what I'm going to do with the suite class is encapsulate that whole process that we just went through. That Bayesian update is wrapped up in a function that I'll show you in a second. So this is the init method. So a suite is a kind of class. One more try. A suite is a kind of PMF. So I inherit all the methods that you just saw for PMFs, and I'm going to add init. So if you give me a list of hypotheses, I'm going to initialize the suite, and I'm going to give the same probability to all of them. That's a common prior distribution, is a whole bunch of hypotheses that are equally likely. If you've got a different prior, you would just override this. And then this is the meat of it. This is the Bayesian update. If you tell me to do an update with a particular set of data, I'm going to loop through all the hypotheses. And for each hypothesis, I'm going to compute the likelihood of the data given the hypothesis. Okay? And that's the conditional likelihood of the data, just written out in Python rather than in mathematics. I'm going to multiply each hypothesis by its likelihood. And then at the end of the loop, I'm going to renormalize the whole suite. Make sense? Now, the only part of this that's possibly confusing is that I haven't given you a likelihood function. In general, the suite class does not provide a likelihood function. The way this works, the suite class is like an abstract parent class. It contains the Bayesian framework. When you want to use it, you extend suite. You define a new class that inherits from suite and that provides the likelihood function. And we're going to see two examples. So over there on the left, dice and euro are two classes that we're going to work with in a couple of minutes. Each of them is a child class of suite. It inherits update, and it provides likelihood. In fact, if you want, let's take a quick look. So let's open up dice.py. And this is pretty much in script form, the same kind of thing that we were just doing on the command line. So I import suite from ThinkBayes. And then, as I said a minute ago, I'm defining a new class called dice that inherits from suite. And all I have to do is provide the likelihood function. And I've given you, for now, a broken likelihood function that just returns 1 all the time. So that's not going to do any good. You're going to fill this in just a minute. Take a quick look at main. So what main does is it creates a new suite. In this case, I'm using integers to represent the hypotheses. So each hypothesis is 4, 6, 8, 12, or 20, representing that's the number of sides on the dice. And I'm going to do an update with the value 6, which is the value that I rolled. So inside likelihood, hypo, the hypothesis, is going to be the number of sides on the dice, the hypothetical number of sides on the dice, and data is going to be the outcome of the roll. And your job is to figure out what's the likelihood of the data given the hypothesis. So to think about that, let's think about this. So if it is a 6-sided die, if the hypothesis is 6, what's the probability of the outcome 6? 1 in 6. Okay. How about on a 10-sided die? What's the probability of getting a 6 on a 10-sided die? 1 in 10. And on a 4-sided die? 0. So in general, what you are going to figure out is what's the likelihood of getting n on an m-sided die. So take the logic that we just figured out, turn it into Python, and put it into the likelihood function. And I will come around and help if I can. Hey.
That's the last thing. So the likelihood of getting a 6 on a 4-sided die would be 0, right?
Correct.
Okay.
Good. Other questions? Things making sense? Hey. Sure.
I didn't get this answer for a while, but I didn't have this for a while. I admitted that.
Ah.
And then, so why would I need these two
Mm-hmm.
to get this
Right.
instead of, like if I comment the size like 0.333 and 0.666?
Yes. Because you're doing two updates, one with the vanilla cookie and then one with the chocolate.
I see. So the other one would have just been like I only had one chocolate.
Yes. I think, yep, that's what you must have computed. Yep. In fact, yes, 1/3 is the correct answer in that case. That looks good. You even got that annoying float that you need in Python 2. I think I'm now in the habit of importing division from future. It's better. Okay, how's that going? Again, you always have the option. For all of these exercises, there's a dice.py, there's also a dice solution.py. So if you get stuck, you can always cheat. Okay. So here's my solution. Yours could look a little different because you could write the sense of the inequality the other way around. But the idea is if the hypothetical number of sides is less than the side you rolled, well, that's impossible, so it has likelihood 0. Otherwise, the likelihood of the data is just 1 over the number of sides on the die. Okay. Again, this is a case where Bayes' theorem is giving you a divide and conquer strategy because figuring out the likelihood function is relatively straightforward. Still takes a little bit of thinking, but once you've got this piece, you don't have to think about it anymore. The Bayesian framework does all the work for you. Yes? 1 over data. Good question. So let's, if I think it's a 10-sided die and I roll a 6, I want 1 over 10, which is the number of sides on the die. No, it's the hypo. The hypo is the number of sides on the die, and data is what you actually rolled. But you just validated exactly what I said, which is that, yeah, you got to think about this one a little until you're comfortable that you got it. But once you are, now you can turn off your brain and let the good Reverend Thomas Bayes come and do all the work for you. So if you run this now, let's exit from Python and run dice solution. So the first part there is after just rolling 1/6, the posterior probability for the 4-sided die is now 0. And that's what we expected. We have ruled out that hypothesis. It can't be true, so it has probability 0. The 6-sided die is about 40%. The 8-sided die is at about 30%. We can look at this in the slides as well. So it's at about 40, 30, 20, and 10, roughly. Okay. Now, on the one hand, that's consistent with our intuition. On the other hand, my impression is that it feels like the posterior probability for the 20 is lower than I expected. Is that true for other people? After only one die, only one roll, we rolled a 6, and we've now concluded that the 6-sided die is about 4 times more likely than, well, maybe 3-ish times more likely than the 20-sided die. So that's interesting. Okay. We could roll the die a few more times. So let's keep the same 6. So take that posterior distribution and now update it with a few more rolls of the die. This is the code that's in dice.py, so we actually already ran it. After rolling 6, 8, 7, 7, 5, 4, well, at this point we've ruled out the 6-sided die. The 8-sided die is certainly looking plausible. 12 doesn't seem crazy, and 20 is at least possible. But if you run the Bayesian update, what you get is this posterior. So yes, 4 and 6 have been eliminated. That's what we expected. We are now pretty confident that it is in fact the 8-sided die, and the 20-sided die has a very low posterior probability at this point. Yes? Good question. How is it factoring in the fact that it has never rolled anything above an 8? And yes, it is taking that into account. One way to think about it, we've now rolled the die 6-ish times. If I got five or 6 pieces of data. We've rolled it 6 times. We've never seen anything bigger than an 8. If it really is a 20-sided die, what would be the chance of seeing that? It would be 8 out of 20 raised to the 6th power. And it's that raising to the 6th power that's gradually ruling out the 20-sided die. That make sense? Cool. Okay, so there's what that posterior distribution looks like. Here's where we are so far. We've done the dice problem. Now we have the suite class, which is this framework for doing Bayesian statistics. And we've written our first likelihood function. We're going to do another one in a minute. But before we do that, we're going to take a break for just a couple minutes. What I'm going to do, we have an official scheduled break at one point where we get to go out and have coffee. I'm also going to have a couple of just informal breaks, so you get a chance to stand up, talk, just stretch out a little bit. But let's resume in just about 3 minutes. So quick break.
This was assuming, it was all assuming that you use the same die every time, right? Just pick one
Yes.
die and same die.
Yes, good point. I should have said that more explicitly. Yep, you got it. Mm-hmm. Are you from Brazil?
No, that's Mexico.
Ah, okay. I was trying to go by accent, but obviously I got it wrong.
Nobody ever guesses my accent.
Very good. Yeah, where in?
Like from California, they guess it.
Mm-hmm. Yep. Where in Mexico? Oh, okay. Yep. Yes. Yep. Yep. Is that where the asteroid killed all the dinosaurs?
Not that close, but we're along with the giant crater, I guess.
Yes. Yep.
We're along the Gulf.
Yes. Oh, very good. Good. Well, welcome. Hi.
Getting the same numbers you were on the first thing with the cookies and the bowls for the second try. So I
Yep.
did
So
you went
there's your prior. Oh, you did. You took away the vanilla cookie.
Oh, okay.
So right. So this is what you solved is the problem of if that first cookie had been a chocolate cookie, then this is the correct solution.
Okay. So oh, okay. I see what you're saying. I got it.
Justin, how are you? I'm Alan Downey. I thought you looked familiar. Good. Good.
Thank you for your long response.
Sure. Sure.
The trains question before.
Ah, right. Good. 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 Things going well so far?
Yeah, that's great.
Excellent.
So if I got to like the 4 chapters of your book, is that about what we're going through in the tutorial today?
Yes, I'm skipping around a little bit. We're going to do hypothesis testing, which is from a later chapter. So at least that part will be new for you. And actually, I forget what's in which chapter.
Okay.
So good.
I read the book straight through, then I'm kind of going through and doing all the examples now.
Oh, great. Very good.
This is great.
I lost them. They're not coming back. Good. Good.
The internal style.
Oh, they switched.
Yeah.
Oh, great. I don't have my excuse anymore. Oh, actually, I have to check. For a while, they had an internal and an external style guide. That might be the external one. Ah, okay. They had switched? I was there in 2009 through 10. Yeah, could be. All right, hopefully if I talk for a couple of minutes, people in the hall will hear me and realize that they should hurry back and get going again. I'm going to get you started on an exercise anyway, so it's okay if people take a minute to come back. We're going to do the train spotting problem. And this is the premise. The premise is a little contrived, but again, this is getting us toward solving a real problem. So the premise is that you know something about a freight carrier. So you have a prior belief about how many locomotives they operate. You don't know exactly how big the company is, but you figure it's between 100 and 1,000 if you had to guess. You see one particular locomotive that's numbered 321, and you assume that the company that's operating these locomotives has numbered them from 1 to n, where n is the unknown number of locomotives that they're operating. And now the question is, based on this data, train number 321, how many locomotives do they have? Again, we can think about the logic a little bit. It's similar to the logic that we were just applying to the dice problem. If you see, again, if they're numbered from 1 to n, and you see train number 321, what's the probability that they are operating only 100 trains? 0. That's been ruled out. And in fact, all of the hypotheses from 0 up to 320 have been ruled out. And now the question is, what are we going to do with the rest of them? And so that's my exercise for you guys. Get into train.py, and you'll see. Yeah. Let me open that up. So in train.py, you see we have, again, a set of hypotheses, which are the numbers 100 through 1,000. I create a suite called train and then do an update with the data. The data in this case is the number of the train that I saw. And again, I've given you the outline of a likelihood function, and your job is to fill in the body of this function. Would you, if you check with your neighbor, he can get you caught up. So if you run train.py, before you modify train.py, if you just run it, it's going to show you the prior distribution. This is the prior, showing on the x-axis the possible number of trains from 100 to 1,000, and on the y-axis is the probability associated with each hypothesis. This is a uniform distribution. They all have the same probability. The vertical axis there doesn't really tell you very much. I think that's just 1 out of 900 because there are 900 or maybe 901 hypotheses. Okay, so let's think a little bit about the likelihood function. We have a similar logic again to what we did with the dice problem. We said anything from 320 down has been ruled out. Let's try one of the other ones. If the train company is operating 1,000 locomotives, what's the probability of seeing train number 321? 1 out of 1,000. Okay, in fact, any train that's less than 1,000. If the train is operating 900, if the company is operating 900 locomotives, it's 1 out of 900. And at some point, I'm hoping an aha moment occurs, which is that you realize it's not just similar to the dice problem, it's actually identical to the dice problem, and the exact same likelihood function will do it. So if you look at my train solution.py, and look at the likelihood function, it's actually exactly the same as the dice problem. And if you run it, let's close that. So again, this is the uniform prior distribution. And if we run it, this is what the posterior distribution looks like. So everything from 320 to the left now has probability 0. The most likely value is actually 321, which is a little bit weird, because if you saw train number 321 and I asked you to guess how many trains they have, it would be a little weird to say, I think they have 321. On the other hand, if it was like a raffle and you were trying to guess how many jelly beans there are in the jar, and you get a prize for getting it exactly right, and getting it wrong gets you absolutely nothing, then actually your best strategy would be to guess 321. A little bit counterintuitive, but true. If you were a competitor and you were trying to scout the competition, and somebody asked you what the average number of trains is that you think they might be operating, then you could compute the mean of this posterior distribution, and that's going to be a little bit higher than 321, and that makes more sense. It seems unlikely that we would just happen to see the highest numbered train that they're operating. And that gets me to the next thing that I wanted to talk about a little bit, which is once you have a posterior distribution, how would you summarize it? So actually, let's stick with that scenario. You work for a competing freight carrier. You have been asked to scout the competition. You come back to your boss and you have to report. You could show the boss the probability mass function, but your boss does not understand probability mass functions. And so you have to summarize it somehow. And there are a couple of ways to do that. These are some of the functions that are built into the suite class. I mentioned the mean a minute ago, so you can compute the mean of the posterior distribution. The maximum likelihood is the single value that has the highest posterior probability. And the credible interval is a range that captures 90% of the posterior probability. And so if you run those, here are the results. Okay. So the mean of the posterior distribution is 597 trains. And again, that kind of, I like the intuition of that. We saw number 321, and that makes us think that they're probably operating about 600 trains. In other words, the one we saw is probably about in the middle of their range. So if I have to make a single value estimate, the mean would not be a terrible thing to report. So you would say, boss, I think they're operating about 600 trains. We talked about the raffle scenario. In the raffle scenario, you would guess 321. If your boss now asks, well, okay, maybe it's 600, but how confident are you? You would give them a range and you say, well, I think there's a 90% chance that the correct value falls between 340 and 945. And that's an honest answer, yes?
Is there some kind of symmetry condition on the confidence, on the credible interval too?
Good question. So the question is there any symmetry on this confidence interval?
There could be multiple intervals, each of which covers 90%.
It could be multiple intervals. And so in this case, the PMF has a shape where the posterior CI will be contiguous, but not symmetric around anything. So how did I pick this one? Oh, so I picked this one. I trimmed 5% off the bottom and 5% off the top. And then I got the middle 90.
I was just curious, why would that ever be more useful than the interval not starting at the most likely?
Good question. So why is this more likely than the one that contains the most likely value? Or why is this a better choice than the one that contains the most likely value? It depends on what you're planning to do with this. And where I'm headed next, we're going to see an example in a minute where you take your posterior distribution and don't just summarize it using one number or two numbers. You actually take the whole posterior distribution and make it part of a decision analysis process. So I think my answer to your question about why would I use this CI is I might not. What I might rather do is use the whole distribution because that's all the information I've got.
Is there actually like a physical meaning to the mean in this example? It's not like we have multiple things that did happen. There's
Right.
like a single truth. So I know what
Yep.
the mean is looking at the graph, but what's it mean in terms of the trend?
Good question. So what does the mean of a posterior distribution mean? For want of a, sorry for the pun, but in this case, there's not a physical interpretation. It is, if you are only allowed to make a single guess, choosing the mean is the choice that minimizes your expected squared error. And so if the cost function of being wrong is proportional to the square of the error, then this will minimize your cost. Good so far? All right. So we did the train problem. One nice thing, if you spot more trains, we can do the update exactly the same way. It's just successive updates. And so as you get more and more trains, the size of that credible interval will get smaller and smaller, which represents your increasingly precise information about how many trains they're operating. Yes?
I guess I feel kind of silly for asking this, but so let's say the next car you see is 550,
Mm-hmm.
and then you see 525. Is the answer still 551? Gotta be, right?
Let's do that. It's a little, there are some pieces of this that are a little counterintuitive. So what numbers do you want to run?
Just 500, make it easy.
Yep,
And then 525.
525. So we have a little bit of a feeling there that because these data are clustered, that feels like it should be different than any other three numbers. But we can run this. So let me run this version, and let's see what the posterior distribution looks like. So the everything below 525 has been cut off. That's what we expected. And this is a little bit pointier than it was before. This drops off a bit more quickly because we've got more data. But
But we know that it can't be, 549, right? Because we saw 525 or 550.
the biggest number we've seen is 525.
Oh, I'm sorry. Yeah, that's right.
Yep.
I just got confused in my head.
Sure. So the shape of this curve is getting pointier. You can think of it as a narrower distribution, and that's good. Narrow distribution means that we are more precise about what we know. But the somewhat interesting thing here is that the maximum value that we've seen, that matters, and the number of trains we've seen, that matters, but the other two values have no effect on the outcome at all. So if I saw trains 1, 2, and 525, the result looks exactly the same. And the summary statistics look the same. Okay. And that's a little bit counterintuitive because if you actually saw 1, 2, and 525, you might be suspicious about our prior assumptions. You might start to question whether they had numbered them consecutively and all that. But if we stick with the prior, if let's say we know that for a fact, then this is the correct posterior distribution. This is what we should believe after seeing the data. Good. Thank you, all good questions. One other question I wanted to get at is why I chose this example. Again, it's kind of an artificial structure. I picked it for one reason, just because we're practicing. We're going to write lots of likelihood functions. I picked it because it's a nice example of inference from very sparse data. I've only seen one train. How do I do anything with that statistically? Classical approaches to statistics don't work well with very small n. And one of the nice things about Bayes is if you have a very small amount of data, you're not going to get a very precise answer, but I can be very precise about how imprecise it is, which is useful. And then the last thing is, although this was a toy problem, it is actually identical to a real problem, which is the German tank problem, which was a statistical problem in World War II. It turned out that the German factories that were manufacturing parts for German tanks were numbering them sequentially. And every time the Allies captured a tank, they would write down the serial numbers, and then there were statisticians who analyzed it. They came up with estimates of how many German tanks were being produced each month. And after the war, when they captured records, they were able to compare the estimates with the actual numbers. If you go to this Wikipedia page, there's some data there that was taken from a paper written after the war. These were a couple of the monthly estimates for the number of tanks the Germans had produced. The statistical estimates on the left were based on a method very similar to what we just did. The intelligence estimate was generated by the spies when they were asked how many tanks the Germans have, and the actual numbers turned out to be very close to the statistical estimates and way below what the spies were reporting. So that was kind of a nice historical example. Good. You guys, I put in slides every once in a while to remind me to stop and see if you have questions, but you guys are being great. You're asking questions as we go. Nevertheless, questions. Oh, that's a good question. So from their posterior distributions, what number were they reporting? I'm not sure. Possibly a mean. Yeah. More likely they gave a range. Good. So I have to tell, I was explaining this to my students, and I said the same thing. I said, well, you should hash those serial numbers. And I have a student in the class who's German, and from the back of the room, he made a joke. He said, oh, thank you, I will pass that on.
In the train problem, we started with the assumption that there were a maximum of 1,000 trains.
Yes.
Where does that come from? Because it really varies the CI.
It sure does. I'm glad you ran that experiment. This is a case where your posterior belief is very strongly dependent on your prior. And if you are less certain about how many trains they're running, it's going to have a big effect. We could run it, so your boss comes back and says, well, your prior was based on old information. We've updated it. We now think they might have up to 2,000. And we can run that. So in the previous example, the posterior mean was about 688. This is after seeing 3 trains. If we run it again with a different prior, it goes up to 831. So this is a case where the posterior is very sensitive to the prior. And what that means is if you're working with a problem like that, what that means is you probably need to allocate more effort to trying to get as much background information as you can to get the best quality prior that you can. Other questions? Eric?
If we were to add more data, say it was you observed train number 4, train number 50, train number 72, are all way much smaller?
Yes.
The maximum?
Yep.
Is the reason that the curve gets smaller because we just haven't observed things that are larger than the maximum?
Right.
The area of the curve gets more pointy.
Yes, good question. So the question is, if we see lots of trains with very low numbers on them, is that why this distribution is getting narrower and narrower, or is it just the number of trains? And it's mostly the number of trains. It's because if it's similar to I've rolled this die 10 times and I've never seen anything bigger than 8, and that makes me think it's an 8-sided die. Same logic here. Well, that was a good time for questions. Okay, We're going to do the Euro problem. I got this problem from David Mackay, who wrote a book called Information Theory, Inference, and Learning Algorithms. It's an excellent book. It's going to be one of the ones I recommend to you at the end. It's available free in PDF, so the price is right. And it is the book where I learned Bayesian statistics for the first time, so I have a soft spot for this particular book. And one of the questions that he uses as a motivating example is the Euro problem. And this is when the Euro coin was first introduced a number of years ago. I forget exactly when this was, and I didn't put it on the slide. Somebody with too much time on their hands spun the coin on edge 250 times and counted how many times it landed heads, how many times it landed tails. It came up 140 to 110, and they thought that that looked like maybe this is a biased coin. Maybe when you spin it on edge, it's more likely to land heads. They took it to a statistician who computed a p-value. So if you're familiar with classical statistics, the p-value is what would be the probability of seeing an outcome like that, an outcome that is as extreme or more extreme than that, if this were in fact a biased coin. And in this case, that turned out to be 7%, which is on the border of being statistically significant. And so the statistician said, the summary from the statistician is, this looks suspicious. This data suggests that this coin might be biased. Okay? And Mackay's question is, from a Bayesian point of view, do these data give evidence that the coin is biased rather than fair? So we're going to approach this. The framework we're going to use, we're going to assign a value x to represent the probability that the coin will land heads when spun on edge. Okay? Now, one of the things that's going to make your head hurt is that we're going to have a probability mass function in a minute that maps from different values of x to their probabilities. And it's going to be confusing. So here's what I'm going to suggest. Don't think of x as being a probability. Just think of it as being a physical characteristic of a coin. So any given coin has a diameter and a weight and some probability of coming up heads, which I'm going to call x. X is unknown, but we're going to estimate it. We're going to do this in 2 steps. So the estimation part is, given the data, we're going to give our best guess about what x is. And then I'm going to come back to hypothesis testing, which is, what's the probability, after having seen this data, that the coin is fair? We're going to use suite again. Now I'm going to define a new class called Euro that also, again, it's going to inherit from suite. So it gets the update function, and all we have to do is write the likelihood function. So open up euro.py and take a look at likelihood. Here's the statement of the problem. So when you get the data is going to be a string that's either H or T for heads or tails. And you're going to get a hypothesis, and your hypothesis is going to be the hypothetical value of x, which is going to be an integer between 0 and 100. And your job is going to be compute, if this hypothetical value of x is correct, what's the probability of getting the data that I got? I'll give you a minute to work on that. As always, if you're completely stumped, just look at the solution, or chat with your neighbor and see if your neighbor can get you unstuck. give you if you're stuck, you can use the hint. So this is one of those cases where it's confusing and it takes a while to figure it out, and then when you figure it out, it's so obvious that it's confusing. So let me see if I can talk through this and make sense of it. We're given the value of this hypothesis, and the hypothesis is from 0 to 100, so I divided through by 100 to turn it into a probability. And what x represents is the hypothetical probability of getting heads. So if the data actually is heads, then we're being asked what was the probability of getting heads if the probability of getting heads is x. And the answer is x. So that's the first part. And then the second part is if the probability of getting heads is x, what's the probability of getting tails? 1 minus x. And that is, in fact, the likelihood function for this scenario. This is assuming that the way I've written it is not very error-proof. I'm assuming that the data is always either heads or tails, and that x is always between 0 and 100. But if that's the case, then this should work. Questions about that? Again, you scratch your head for a while, but then once you got it, it's relatively simple. And again, once you've got it, you can turn off your brain, you can stop thinking. The good Reverend Thomas Bayes comes in and solves the problem for you. If you scroll down, you'll see that what it currently does is it creates the suite, and the prior probability is going to be uniform from 0 to 100. So I'm saying before I looked at the data, I had no idea what x was going to be, and I'm going to assume that any value from 0 to 100 is equally likely. That might seem crazy. We probably don't really believe that about coins. If you looked at an ordinary coin that's not like a crazy shape or anything, it's relatively flat, it's got engraving in it, what's the chance that that x is like 1 or 99? It would be hard to make a coin that's a normal shape that has a 99% chance of landing heads. On the other hand, would you believe 51? Yeah, sure, I believe a coin could be that biased, particularly spun on edge. I think if you toss a coin in the air, I think people have done studies that say, even for coins that are a little bit funny shaped, still, but if you spin it on edge and wait for it to fall over, I believe that a lopsided coin might be more likely to go. And 51% doesn't seem crazy to me. 60 is not out of the realm of possibility, but 90 does not. Okay. My point is that choosing this particular prior, a uniform prior, is probably not a good choice at all. We're going to come back in a minute and see what happens if we choose a more reasonable prior. But for now, let's just stick with simple and easy to implement. So that's my prior. I'm going to do an update with just one H, and let's see what we get. 1 heads. There we go. That's the posterior distribution after seeing 1 heads. So one thing to notice is that now the posterior probability that x is 0 has become 0. Because we've seen a heads, so we're guaranteed this coin must be capable of producing heads. And the most likely conclusion is that it's a double-sided coin, or a double-headed coin. So the most likely posterior value of p is 100, and it's a straight line in between because the likelihood function that we just computed is in fact a line. It's linear in x. So that's after seeing 1 heads. What do you think it's going to look like after 2 heads? Think about it for a minute and then run it and see if it looks like what you thought. It's starting to get a little bendy. So the low values of x are getting less and less likely. If this coin had only a 1% chance of being heads, then seeing 2 heads would be surprising. And the high values of x are looking more and more likely. Anybody know what shape that curve actually is analytically? That is a parabola. We just took something that was a constant and we multiplied it by x and we got a line. Then we multiplied it by x again and we got x squared. So this is an example where doing this problem analytically is actually very easy. We're being a little bit silly by doing it computationally. Let's do one more. What if you flip it again or spin it again and the next one is tails? So what effect is that going to have on the prior? Okay. So the posterior probability that x is equal to 100 has now become 0. We've ruled out that hypothesis because we just flipped a tail. So the extreme values have now been ruled out, but it's still, the bulk of this curve is still on the right-hand side, which means that we still, having seen 2 heads and 1 tail, we still think that x is probably large. And in fact, the maximum likelihood value of that is 66%, 2/3, which is the ratio that we've actually observed. Good so far? Okay. So if you want, you can now put in, we've seen that. That was the prior. There's what it looks like after 1x, after 1 heads. 2 heads. 2 heads and 1 tail. And now if you want, why don't you put in this loop? Why don't you add in, let's say that we've seen 7 heads and 3 tails. You could try that out. So there's what it looks like after 10 coin tosses. And it's getting narrower and narrower. And again, a narrow posterior distribution is a good thing. That's telling you that you are becoming more and more confident about what the actual value of x is. And then finally, if you load up Euro solution, URO, I thought Euro solution already had this in there, but it doesn't, so we'll do it live. So we're going to create a list that has h times 140 plus t times 110. And we'll do that update. So this is the data set that was actually reported in the newspaper article: 250 spins, 140 heads, 110 tails. And let's see what the posterior looks like. There it is. Again, getting narrower and narrower, and still a bit higher than 50%. And the peak is the actual observed rate, which is, I think, 63% or something near there. And that's that. We have the same problem that we had with the train, which is to figure out how to summarize this thing. And again, the question that we're asking is whether this coin is biased or fair. So one way that you might think is, well, we could just ask, I've got this posterior distribution, and we could say, well, what's the probability that x is 50%? You can ask that question. It turns out not really to be the right question. So you get an answer, 0.021, but then you realize that we did kind of a funny thing. We took the value of x. The value of x is a continuous value that could be anything between 0 and 100. We chopped it up. We discretized it into 101 possible values, and that posterior probability just depends on how we chopped it up. If you have more hypotheses in the suite, then that probability gets smaller. So it's clear that that probability isn't really answering the question we wanted, which is whether the coin is biased or not. You can pull out the maximum likelihood value. That turns out to be 56%. The mean is also about 56%. As you have more and more data, the posterior distribution becomes symmetric, and the median and the mean converge on each other. Credible interval works out to be somewhere between 51% and 61%, which means according to this posterior, the chance that the actual value is 50% falls outside of your 90% credible interval. So that's interesting. That does suggest that the coin is fair. Suggests that it's biased. I just got to skip this. It's a little bit of picking on the frequentists that we don't need. But it's still not answering the question that we want. We're going to come back to it in a minute. Before we get to hypothesis testing, which is where we're headed, I want to take a quick detour on what I promised, which is to talk about the prior. So I said a minute ago, what we know about coins, the uniform prior is probably not a very good choice. So we could do an experiment with a different prior. And one possibility might be something like a triangle-shaped prior. So this is capturing the notion that I don't actually think you can make a coin that has a 0% chance of landing heads, other than if it had two sides that are actually different from each other. I think 100% is unlikely, and the most likely thing is close to 50-50, so let's try that as a prior. What do you think that'll look like? If I have two different priors, my blue and my green, what do you think the posteriors will look like? They end up looking like that. Remarkably similar to each other. And you can try this out with a number of other priors. They all come out pretty much the same. You can see there's almost no visible space between the blue and the green curves there. This is an example of what's called swamping the prior. And the theory is that if you have enough data, your posterior distributions will eventually all converge at least close to the same posterior. So even people who start out disagreeing with each other will eventually get close enough that they pretty much agree. They never actually mathematically converge, but the difference can be small enough that it doesn't matter for practical purposes. With one exception. If you start out with a prior probability of 0, if you have ruled out a hypothesis, then there's no amount of data that will change your mind. You could start out with a very small number, and it doesn't matter how small it is, eventually there will be enough data to persuade you. But if you go all the way to 0, you're done. You become immune to data. And that's the basis of what's called Cromwell's rule, which is kind of a rule of thumb in Bayesian statistics, which is that you should be a little bit generous about your prior distribution. Try not to assign 0 to anything that's at least in the space of possibility. And the reason it's called Cromwell's rule is that this was Oliver Cromwell's speech in the Parliament, in which he said, "I beseech you in the bowels of Christ, think it possible that you may be mistaken," which is a little bit overblown, but it's a good thing to remember in Bayesian statistics. Yes?
When you say avoid 0, does that mean avoid including 0 in one of your possible hypotheses, or avoid only thinking that it is 0?
Good. So the question is, are you assigning 0 as one of the hypotheses. Oh, sorry, no, it's okay. It's okay if one of your hypotheses is that x is 0, that's fine, but don't assign a prior probability of 0 to any of your hypotheses. And it's the same thing. Giving a prior of 0 to a hypothesis is the same as removing that hypothesis from the suite altogether. Okay, so just to summarize what we've done, if you want to estimate a value, you start with a suite of hypotheses that represents all the possible values. You choose a prior distribution by assigning a probability to each hypothesis, compute the likelihoods, multiply through, and then again, you can stop thinking at that point. Bayes will do the rest, you get the posteriors. So that's what that framework looks like. Let us take our mini break number 2. Before we go, do I remember there's an official time when we are supposed to go get coffee? Does anybody know when that is? All right, I will. 2:50. You know what time it is now? 2:52. Let's go get some coffee. So we'll come back in about 10 minutes. Okay, onward. So I skipped over something that I now want to come back to, which is I did a little bit of a bait and switch. I started with the question, is this coin biased or not? And I substituted in an estimation problem. So we estimated the most likely value of x, or we have the posterior distribution for x, but I didn't really answer the question that Mackay posed. What he asked is, do these data give evidence that the coin is biased rather than fair? To answer that, I have to start by asking, what does it mean to say that the data are evidence for or against a particular hypothesis? This is the usual framework. In a Bayesian framework, this is what that means is we would say that D is evidence in favor of H if the posterior is larger than the prior. If the data make the probability go up, then they are evidence in favor. So the top line says the posterior is greater than the prior. That will be true if the likelihood of the data under H is higher than the likelihood of the data under not H. And if you divide through, you get the bottom formulation, which is the most common way that this is written in a Bayesian framework, which is the likelihood ratio of the likelihood of the data under H divided by the likelihood of the data under not H. If that ratio is greater than 1, then we would say that D is in favor of H. If it's less than 1, then D is against H. That ratio, the likelihood ratio, is also called the Bayes factor, and it's a measure of how strong the evidence is. So if it's exactly equal to 1, then that means that the data were equally likely whether H is true or not, and that means that the data don't tell you anything about H at all. If that ratio is high, that means that your data were much more likely under H than under the alternative, and therefore your confidence in H goes up. If that number is very small, your confidence in H goes down. Make sense? So that's the Bayes factor. And that defines what it means to say that the data are evidence. So here's where we're going to go with this. We're going to have two hypotheses, the hypothesis that the coin is fair or the hypothesis that the coin is biased, and we're going to compute those two terms. The likelihood ratio is the probability of the data under hypothesis F and the probability of the data under hypothesis B. The first one is easy. If the coin is fair, then X is exactly 50%, and it's really easy to compute the likelihood of the data if X is 50%. The second one is hard. What does it mean to say, what would be the chance of seeing this particular outcome, the 140 heads and the 110 tails, if B is biased? I don't know how to answer that question because you haven't really told me what biased means. It's a little bit like having a barroom bet. Like you think it's fair and I think it's biased, so we start challenging each other like, well, all right, how much do you want to bet? The next question you would ask is, well, now, hang on a minute. What exactly do you mean when you say biased? Because I'm not betting until you get more specific. Now, there's one really obvious cheat, which is that I could choose my definition based on the data. I could say, look, I've seen 140 heads. I've seen 110 tails. So X is 140 out of 250, 63%, something like that. That's my theory. My theory is that the coin is biased with X equal to 63%. And again, in my barroom betting scenario, I suspect that you would not let me get away with that. Having cheated at the data, first of all, it seems strange to use the data twice. I can't use the data to define my hypothesis and then use the data again to evaluate my hypothesis. That doesn't seem right. The other is something is obviously wrong here, because if you do this, then you would conclude that practically any data supports B. F would not do very well under this strategy. So it's clear that we're going to need some rules before we're ready to place the bet. And so I'm going to propose the following rules. One of them, you have to pick your hypothesis before you see the data. You're not allowed to use the data twice. And the other is you can have a suite of hypotheses. In other words, you don't have to tell me exactly what X is. You can give me a range of possible values for X. So you could say, I think the coin is biased, and I think X is between 50% and 70%. or between 50 and 30. It's fine to give me a range. In fact, you can think of that as being a prior belief about X. But if you pick a range, then I'm going to compute the weighted average of the likelihoods. And these two rules, by the way, these are the same as the rules of roulette. So first of all, you have to place your bets on the table before the ball stops spinning. It seems pretty obvious that you can't wait for the ball to stop and then bet on 17. They will throw you out if you try to do that. The other thing is that you're free to bet on as many squares as you want, but for all the credit you get for winning, you also have to pay the price for losing. So if you put everything on one square, then you're kind of all your chips are in one place. You can spread it out, but you pay a price for spreading it out. So here's how I'm going to do that. This is the average likelihood function. This just says you're going to give me a suite that represents your definition of what biased means. Again, it could be a range from 50 to 70%, and you're going to give me some data. I'm going to compute the average likelihood of the data under all of the hypotheses in your suite. And I'm going to do that just by looping through each hypothesis. I'm going to compute the likelihood of the data under each hypothesis, and I'm going to compute the weighted average, where I take the likelihoods, multiply by the probabilities, and add up the total. So if there's only one hypothesis in your suite, then this loop only runs once and evaluates one likelihood. You could do two. You could have two hypotheses and give them a 50-50 balance, whatever you want to do. Okay? So let's start out with a simple definition of F and a simple definition of B. I'm going to say, so F means coin is fair, and that means that X is 50%. I'm going to give B all the other values of X. So if you say the coin is biased, one interpretation of that is, I don't know what X is. X could be any value between 0 and 100, but not 50. Okay. Again, probably not the most sensible definition of B, but that's where we're going to start, and we'll go from there. So fair is going to be the suite that represents the fair hypothesis, and it only has one value in it, 50, and the probability associated with that is 100%. This is the biased hypothesis. I'm going to loop through all the values from 0 to 100. If X is not equal to 50, I'm going to put it into the suite, and then I'm going to normalize the suite. So this represents a uniform distribution for X with a little notch cut out of it that says, I don't think it's 50%. And then I'm going to compute the average likelihood of those two. To do this, I'm going to change the representation of the data a little bit. In the previous version, we used the strings H and T. In this one, I'm going to use a tuple that is the number of heads and the number of tails. So it's a little bit more compact. We're going to see what the likelihood function looks like in a minute. In fact, if you'll start up euro2.py, the main function is exactly what we were just looking at. So the main function creates fair, which represents the fair hypothesis, biased. The data is represented by a tuple. It computes the two average likelihoods, and then it computes the ratio of the two, which is the likelihood if it's biased divided by the likelihood if it's fair. So let's take a look at the likelihood function, then we're going to come back and look at this for just a second. There's the likelihood function. Yes. Is this the right thing? Oh, sorry. That's average likelihood. No wonder I was confused. Here's the likelihood function. So again, X is the probability of heads, so it's the hypothesis divided by 100. The data, the variable named data, is a tuple that represents heads and tails, so I'm going to unpack it into two variables called heads and tails, and then I'm going to compute X raised to the power of heads times the number of, 1 minus X raised to the number of tails. You might recognize that as the binomial probability distribution. I've left out the binomial coefficient for reasons that I will explain if somebody asks later, but for now, take my word for it. Good so far? All right, so I've got my likelihood function, I've got my average likelihood, and I'm going to compute the Bayes factor, which is also known as the likelihood ratio, which is the likelihood of the data if the coin is biased, divided by the likelihood of the data if the coin is fair. And now here's my hard question for you. If that number comes out to be greater than 1, let's say that it comes out to be 5, what would that mean? How would you interpret that number? Five times more likely to be biased than to be fair. That's pretty much correct. I could quibble a little bit with the wording, but I'm going to say yes. That's right. So if this thing is larger than 1, that means that the data are evidence in favor of the biased hypothesis. And if it's less than 1, that means the data are in favor of the fair hypothesis. So let's run it and see what we get. And this is euro2.py. Okay. Let me actually look at this on the slide. It's a little bit easier to read. There we go. Are you all able to run it? And it generates numbers that should look like that. We're gonna modify Euro 2 in a second, so you'll want to have a working version of this. So the probability of the data, if the coin is biased, turns out to be 2.6 times 10 to the minus 76, which is a very small number. And what that means is the probability of seeing this particular outcome is quite small, and that's often true for any particular outcome. The probability of the data, if the coin is fair, also a very small number. Those small numbers all by themselves don't mean very much. It's really only the ratio between them that means anything. And the ratio in this case turns out to be about 0.47, which is less than 1. And what that means is that these data actually are evidence against the biased hypothesis. These data are in favor of the hypothesis that the coin is fair, which is a little bit surprising. 140 heads and only 110 tails is pretty lopsided, but nevertheless, the fair hypothesis does pretty well, at least when we compare it to a stupid definition of B. Okay, so we kind of stacked the deck here a little bit by choosing a not very good definition of B. And that's what I want you guys to do next, is pick a better definition of B and plug it into euro2.py, and let's see what that ratio comes out to. If you have some ideas about what you want B to be, that's fine. You can code it up yourselves. If you want to use mine, you can. So this is a triangle shaped. This is the same as the triangle prior that we looked at before, except that I left out 50%. So feel free to try mine if you want. You can substitute this into Euro 2, or if you've got a different prior that you think is a better choice, plug that in. I'll give you a couple minutes to work on that. And euro2 solution.py has my version in it. This is the triangle prior. The camera. So this is my alternative definition of B, and I forget whether I cut the 50% out of the middle or not. It turns out it makes very little difference one way or the other. So this is maybe a better definition of B, and if we compute the likelihood ratio with this definition, now it comes out to 0.83. The range was from 0 to 100 still, but it was just a triangle shape. So the 50% had the highest likelihood. All right, so this is a better definition. This is a more fair definition of B, but the likelihood ratio is actually still less than 1, which means that by this definition, the data are still in favor of F, although very slightly. When you have a Bayes factor like this that is very close to 1, it's effectively saying that the two hypotheses are equally supported by the data. The data are not going to move your prior very much. Okay. Did anybody try out, was there a different B? Did anybody manage to come up with a B where the Bayes factor is greater than 1? You got one? Yep, from 20 to 70. Yeah, so a narrower range will tend to do better. This definition of B is getting punished a little bit for those extremes. The stuff that's near 0 and the stuff that's near 100, those values are so unlikely that that suite is getting punished. So if you zoom in a little bit, or if you suspected that the coin was biased toward heads, if you were willing to make a bolder prediction and say, I'm pretty sure that it's greater than 50%, then you could have something like this. So let's take out the low values. If your definition of B was, I'm pretty sure that it's biased toward heads, and I think it's most likely to be near 50%, here's what that's going to look like. So notice that the x-axis has now changed. So this is just from 50 up to 100. So this is the definition of biased where you are being more specific. You are saying, I think the coin is biased toward heads. And in that case, I haven't actually run this, but it actually does what I thought it probably would, which is that the Bayes factor is now greater than 1, which means that if that's what you meant by biased, then the data are in your favor. Make sense? All right. And this is consistent with the trade-off between the more specific your hypothesis is, the more you will be rewarded if you're right, and the more you will be punished if you're wrong. If your hypothesis is wishy-washy, then it will be relatively immune to data because nothing will contradict you if you are not specific. All right. So to summarize where we are so far, the bottom line is that these data constitute weak evidence for pretty much any definition of B. Any Bayes factor that's between about 50% and 2 constitutes pretty weak evidence. Depending on exactly how you define B, you can make the data speak in favor of or against F. And as I said, it's weak either way. That's it for the Euro problem for now. Good so far? Questions? All right.
If you set 56 to be kind of high, then you got a really big Bayes factor.
Yes. Yeah, if you cheat and you set B to be focused right around the 63% that actually came out, then yes, you can get B to be pretty high. Or you can get the Bayes factor to be pretty high. Yep.
How do you trust people when they come with Bayes factors that they're just cheating on stuff?
Oh, so the question is, if someone now reports a Bayes factor to you, how do you trust them? And I think it is, you have to look at the definition of the hypotheses. If people don't frame the hypotheses in a way that makes sense, you would not accept their results. And that's, again, thinking about the barroom bet scenario, you need to agree on your terms before you start computing Bayes factors. Good. We had a relatively short segment there. Should we take a break, or do you want to forge on for one more minute? Or for a few more minutes? Take a break? Forge on. Forging. Yes? Right. Good question. So could you put all of this into a framework with a test set and a training set, or not in that order, and then use that to calibrate your prior? Yes, you could. So all of these, if you're in a predictive framework, you could put this into something like that and use it to choose the prior that works best on your training set and then try it out on your test set. You would probably want to parameterize the prior with just a few knobs so that you're not in danger of grossly overfitting. But yes, all of this would fit nicely into a framework like that. So the question is, how would you apply that to the coin problem? If your goal is to make good predictions, then that framework works well, because what that framework is saying essentially is, I don't care about the truth. I only care about whether my predictions are good or not. And so, yeah, the whole training testing framework is good for prediction. It's not so good for science. If the question that you're asking is like a scientific question, if I want to know the truth of it, is this coin biased or fair, then the machine learning framework is not exactly what you want. I think the Bayesian framework is, and actually one of the books that I'm going to recommend is, well, when I get to it, I'll remember which one I mean. I forget the exact title. But it is taking this notion of Bayesian inference and applying it to the logic of scientific exploration. So let me come back to that if you'll remind me when we get to it. Okay. I want to do one more problem where you guys get an exercise to do. This is an application of what we just did. It's very similar to the euro problem, except that instead of having one coin, I've got two coins and I want to compare them to each other. And this again is going to be an example of using a Bayesian analysis as part of a decision-making framework. So my premise here is sort of a joke, mostly. But if you imagine two people talking about their SAT scores, and Alice says, what'd you get on the SAT? And Bob said, well, I got a 760 on the math section of the SAT. And Alice says, well, I got a 780. I guess that means I'm smarter than you. And my question is that true? Can Alice really make that claim? As usual, we have to do a little bit of definition of what we mean. So by smarter, I'm going to say every person has some ability to answer SAT questions. I'm going to say that they have this mysterious quantity called X, which is their probability of answering any given SAT question correctly. So each person has this attribute. So X sub A is Alice's probability of getting it right. X sub B is Bob's. And what we want to know is what's the probability that X sub A is greater than X sub B. Make sense? So forget about all that whole smarter stuff. I'm just talking about ability to answer SAT questions. The Bayesian approach to this, as always, is we're going to treat X as an unknown random quantity. We'll start with some prior distribution. If I don't know anything about you and I have to guess your quantity of X, what would I believe? And then I'll use the data, your test score, to update my belief. And now I'm going to have two posterior distributions, one for Alice, one for Bob, and I can compare them. This is an example where I don't have to invent a prior. I can actually get the prior by going to the College Board webpage, because they publish the distribution of raw scores for the entire population of test takers. So if I don't know anything about you, I would assume that you are drawn at random from the population of test takers, and therefore my prior belief about your X is the distribution of raw test scores. It's a slightly funky distribution. It's jaggy in a weird way. Does anybody happen to know why it's jaggy like that? It is empirical. So this is actual data. This is from 2009, the offering of the test. You might remember, if you took the SAT some time ago in your past, that you get penalized for an incorrect answer, and therefore there are particular values that are a little bit easier or a little bit harder to get because of that round off, and that's why it's jaggy. If we wanted to be a little bit careful with this data, we might smooth that. It's going to turn out not to make any difference, so it's just fine. Okay. Again, I need a likelihood function, and my the way I'm going to set this up is when I get a hypothesis, the hypothesis will be a hypothetical value of x. So this will be your probability of answering any given question correctly. The data will be your score on the SAT, and that's the value that's between 200 and 800. Those values are your scaled scores. So in order to apply this framework, I have to map that onto your raw score. And the nice people at the College Board also publish that data. So I can look up, if you got a 760, then that means that you got, let's say, 52 correct out of 54 questions. And that's what the reverse function does. It does the reverse scaling, and it computes the raw score. Once I've got the raw score, I can figure out the yes, no. How many did you get right? How many did you get wrong? And then the likelihood of the data is x raised to the ones that you got times y, 1 minus x, raised to the number that you got wrong. Does the likelihood function make sense? This is the same likelihood function we were just looking at in euro2.py. Good? All right. And there is what the posterior distributions look like. So remember that the prior, let me just go back a couple. The prior looks like that. It's between 0 and 1, and it's not a normal distribution. It's not a bell-shaped curve, but it has kind of that shape. Most people are in the middle, not too many people at the low end, not too many people at the high end. However, if you get a 760 or a 780, then I start to think that you are probably at the high end of that curve. I've pretty much eliminated the low and middle end. And for both Alice and Bob, I'm pretty confident that your chance of getting an SAT question right is 80% or better, and in fact, likely to be in the 95-ish range. So those are the distributions for Alice and Bob after I know their SAT scores. And now I want to answer the original question, which is what's the probability that Alice's value is greater than Bob's? And that is what you are going to do. If you look in sat.py, you will find a function called PMF prob greater, which takes as arguments two PMFs. And your job is to compute the probability that a random value drawn from PMF1 is greater than a random value drawn from PMF2. We'll take a look at the file, and then I'm going to give you a hint on how to do this, because you don't have enough information yet to be able to do this. So if you like, take a minute to look over this file. This one is a little bit more involved than the other examples because I have to read some data. So there are two CSV files that I downloaded from College Board. So I have to read those. I have a function in there that does interpolation. I have to be able to do the reverse mapping from scores to raw scores. So there's a little bit more machinery. And you are going to fill in this piece, which is the probability. And did I use a different name in the two places? No, PMF prob greater. Yeah. So I'm going to walk you through a little bit of pseudocode. So here's the idea. Remember that each PMF is a map from a possible value of x to its probability. So if I want to know whether a value from one PMF is likely to be greater than another one, what I could do, there are actually a few different ways to do this, but one of them is to iterate through all the pairs and check for each pair whether the one from PMF1 is greater than the one from PMF2. And if so, then I'm going to accumulate the total probability of all the winning pairs. I'm not sure I said that particularly well, but does that make sense? I'm going to give you one more helpful piece of information, which is that if you want to loop through a PMF, you can use the items method. And the items method is going to give you all the x's and their corresponding probabilities. So if PMF1 is for Alice, then x1 is a value drawn from Alice's distribution, and x2 is a value drawn from Bob's distribution. All right, I'm going to let you work on that for a little bit. I'll come around. And as always, if you're stumped, you can cheat and look at the solution. got a partial solution there if you want to cheat. Did I overhear? Is there an error in the code or the doc string? Oh. Sorry. Oh. I'll double check it in a second. So just to clean up one error, the doc string for this function said the opposite of what it was supposed to. So PMF prob greater should be the probability that a value from PMF1 is greater than a value from PMF2.
It's right on the slide.
So it's correct on the slide, but wrong here. Okay, good. Well, half good. Okay, so now I'm going to iterate through all the pairs. And so x1 is drawn from PMF1. So if x1 is greater than x2, then that's one of the examples that I want to count. And now I want my total to add up all of the probabilities for the successful cases. So if the chance of getting x1 is p1 and the chance of getting x2 is p2, what's the chance of getting this particular pair? P1 times P2. That sounds like a good choice. What assumption am I making there when I just multiply those two probabilities by each other? That they're independent of each other. And in this case, I'm comparing two people. I'm saying if Bob's particular value of x is this, and Alice's particular value of x is that, those are pretty independent of each other. So that's a reasonable assumption in this case. And that is what my function looks like. Let's run it. So those are my posterior distributions again. You'll notice that they overlap quite a lot, which means that it is actually possible that Bob is smarter than Alice and got unlucky, or that Alice was particularly lucky on that day. They overlap quite a lot, but as we would expect, Alice's posterior distribution is shifted a little bit more to the right than Bob's. And then numerically how that comes out is the chance that Alice is smarter, again by this definition of smart, is about 61%. The chance that Bob is actually smarter is about 28%. And there's a little bit left over, which is that they might be tied. And that tie is a kind of an artifact of the resolution of the measurement scale. So you could deal with that in a couple of different ways. One possibility would be to take the leftover, the tie, and just divide it by 2 and split it between Alice and Bob. Or what you might say is that that tie is actually possible. Maybe they are equally smart according to this test. In other words, this test cannot discriminate between the two of them. And if the question that you're asking is, can we say with confidence that Alice is smarter than Bob, then maybe this is the right answer. You would just say 61%, and in some sense you would give a tie to the null hypothesis, that they are equally smart. So that's the answer in this case. It turns out that 20 points on the SAT doesn't tell you a huge amount about the difference between two people, which is good to keep in mind if you happen to be on the admissions committee for a college. A couple of points on the SAT, you shouldn't take it too seriously. Any questions about this example? Yes? Yes. Ah, that's a good question. So we iterated through 2 PMFs. We added up a total probability, and I think what you're suspecting is that it might not be normalized. It kind of feels like, are we really sure that that thing is a probability? It turns out that it is. There is a little algebra that we could do to show that the result is a properly normalized probability. One way you could persuade yourself of that, one thing you could do, you could take these two distributions and you could form a new distribution, which is the distribution of the difference between them. And then you would be able to see computationally that the result is a normalized distribution. And then you could just add up the probability that that difference is greater than greater than 0. Yep. Good. Okay. Part of the reason I wanted to do this example is to show a case where we're doing a Bayesian step, which is starting with a prior, updating the prior, you get a posterior, but then very often you end up doing more stuff with your posterior distributions in order to guide a decision-making process. So that was one part of the reason for this example. The other part is that we're taking gradual steps from toy problems that are really well defined. Like, if I roll a 6-sided die, the chance of getting a 6 is very, very close to 1/6. I didn't have to do a lot of thinking about the real world, simplification, abstraction. It's a toy scenario. This is a case where we had to make some modeling decisions. We made some simplifications. In particular, the SAT is designed so that not all the questions are equally difficult. So I started this by saying that every person has some probability of answering an SAT question correct. That would be fine if all the questions were equally difficult, but they're not, and they're not supposed to be. There is an alternative to this, and so one of the things that I wanted to do in the book is an example of a modeling process where you start with some simple assumptions, you get a result, and then you want to know how reliable that result is. One way to do that is to try a more complex model and see whether your results hold up. If the more complex model is very different from the simple model, that means that you need to think more about modeling. If they come out consistent, then that's evidence that your simple model is probably good enough in reality. In the book, it turns out that the complex model does not make a huge difference, which is good news. That means we can get away with a simple model. Just a reminder, for any given physical system in the world, the chances are that there are several reasonable models, and you need to think about your modeling decisions. It depends on what you're planning to do with the model, and it depends on how precise you need the answers to be. But one thing to remember is that the modeling decisions that you make often have a pretty big effect on the outcome. If you look at all the sources of error, modeling assumptions are usually your biggest source of error, as opposed to numerical approximation, for example. People have a little bit of a tendency to focus on numerical approximations and forget about their modeling decisions. If your model is coarse, you can afford to be a little bit fast and loose with the numbers. One of the examples I make of this is there's no point in being super precise about measuring something that is only approximately correct. And my favorite example of this is in the NFL. If you are a fan of football, you will probably see someone get tackled, and there's a pile of people around, and the referee has to decide, or umpire maybe, has to decide exactly where to spot the ball. And that's a pretty approximate, plus or minus a yard or so, or a meter since we're in Canada. Plus or minus a meter, the ball gets spotted. And then if they're not sure whether someone made a first down or not, they bring out the chains and they measure very precisely down to an inch something that was approximate plus or minus a yard. So that's a silly example of one of the things I'm talking about here is mistaking the map for the territory. Don't forget about your modeling decisions. Don't forget that all of your results are based on those decisions. Don't sweat approximations, and iterate. Again, start with a simple model, see how the results look, and then ask, of all the assumptions that I made, which ones are most likely to be problematic, and then do some exploration to see what the cost is for each of those assumptions. All right. I think we waved off the last break. Let's not wave off this break. Stand up, stretch out, just about 3 minutes. So we'll come back at 3:55. Okay, we're back. So I have here this nice relaxing slide, and what this is intended to convey is that the work for you is pretty much done. I don't have any more exercises for you. I have one more example that I want to show you, but I'm just going to present it. You don't have to do any work. So you can relax, take it easy. You've done an excellent job. I appreciate your efforts. I'm going to present the red line problem. This is a problem that occurred to me a couple of years ago. I was commuting, and I was taking the commuter rail into Boston, and then the Red Line subway in Boston from Boston to Cambridge. I was going to Kendall Square. So on my reverse commute, I would have to leave work, and I would get to Kendall Square to try to catch the 4:40 train. If I caught the 4:40, then I would get to South Station on time, and I would get my train home. And what I found myself thinking about, when I got to the platform, if there were only a few people waiting when I got to the subway platform, then I would think to myself, oh, I must have just missed a train, and so I would expect a long wait. If I got there and there were a medium number of people there, then that's good. That means it's been a while since the last train, and so there should be another one along pretty soon. But if there were a lot of people on the platform, like way more than usual, then I knew that something had gone horribly wrong, the trains were not running on schedule, and so I would have to go back upstairs, catch a taxi in order to get to South Station and not miss the commuter rail to go home. So what I wanted to do from a Bayesian point of view was to, again, quantify that intuition. And I'm going to do this in 3 inferences. So the first one is, I need to know the arrival rate of passengers so that I can infer from the number of passengers on the platform how long it has been since the last train. And if I know something about the train schedule, and I know how long it has been since the last train, then I can infer the time until the next train. And if that prediction exceeds the allowed time in my schedule, then I know I have to go upstairs. So that's what this is going to look like. So part 1, I collected some data. The red line provides a web API for collecting historical information. And so I picked the time of day when I was doing this commute, and I found the time between trains for, I think I did about 3 weeks of data, so I observed a few hundred trains, something like that. But I had to make an adjustment to the data. And the reason is that there's an interesting observer effect. If the time between trains varies, then the expected time that's observed by a random arrival on the platform is different from what the MBTA would report. So one way to think about that, here's the example. If, let's say that the trains alternate, and they either come every 5 minutes or every 10 minutes. If you ask the MBTA, what's the average time between trains, they would tell you, well, there are just as many 5-minute gaps as there are 10-minute gaps, so the average time between trains is 7.5 minutes. But if you survey passengers and you ask them for the size of the interval that they arrived in, you would find that more people arrived during a 10-minute gap than during a 5-minute gap. In fact, twice as many. And the weighted average of those intervals is 8.33 minutes. So passengers will observe longer times between trains than an observer of the system would see. So this is, I got my 3 weeks of data. I'm going to use Z to represent the time between trains, and I'm going to use ZB for the biased view that you would get as a random arrival. And this is what those distributions look like. So Z is the darker blue on the left. And what you see is a little bit, well, the dominant mode is at about 7 minutes, and that's the advertised schedule at this time of day. There's a little bit of a bump over there on the left, which is the tendency of trains to get bunched up. And so the intervals are often shorter than the average. And there's a corresponding bump up there at around 15 minutes, which is when the trains are spread out on the track. The biased view of the whole thing is the light blue distribution, and that the whole thing is shifted off to the right. And what that means is, again, you are more likely, even though there aren't very many long gaps, you are more likely to arrive during one. And, well, it's very nice that there are those short gaps between trains, but you're very unlikely to hit one. Okay, so the whole thing is shifted off to the right. Okay, so the next step is to figure out if the time between trains has a particular distribution, then what wait time should I expect? This is actually not a Bayesian thing at all. This is just doing algebra with distributions. If the trains were always equally spaced, if the space between trains was exactly 10 minutes every single time, then what would the distribution of wait times look like? You know it's always you know it's always a 10-minute gap. You arrive at a random point during that 10-minute gap, and so it's from 0 to 10, and it's uniform from 0 to 10. You're equally likely. So if I don't know how big the gaps are, what I can do is I can make a mixture distribution. Let's say it's either 5 minutes or it's 10 minutes. If it's 5 minutes, then it's uniform from 0 to 5. If it's 10 minutes, then it's uniform from 0 to 10. And I can make the mixture of those two distributions. And that's the next piece of this. So I'm adding a new variable here, which is y. So y is the wait time when I arrive in the middle of one of these intervals. The other two curves are the same as what we were looking at before. So dark blue is z. Medium blue is zb, the biased view. You can think of the cyan curve there, the wait time, is kind of like half of zb, smoothed out a little bit. So actually, my probability of having a short wait time is pretty good. The probability of waiting longer than 15 minutes is quite small. All of this is good news. This means that the train usually runs pretty well. OK, now here's the Bayesian part, which is I want to try to infer x. So x is going to be the time since the last train, and this is where I'm going to use the passengers on the platform. So my prior distribution for x is the distribution of x before I see the data, and the posterior is the distribution after I've counted the number of passengers on the platform. So we'll run a quick example of this. So I arrive and I see 15 passengers. I don't actually have to count all the passengers. What I could do is I could have a sample. I could choose one section of the platform. There's a tile pattern on the floor, so I could easily mark out a section. And I could stand there with a stopwatch and count the number of people who come and stand in my zone during my wait time. And let's say that I've estimated that the number of arrivals in my zone is about 2 per minute. And I see 15 people there. How long do you think it has been since the last train? Probably 7.5 minutes. Okay, so, and again, if you had to make a single valued guess, you'd say 7.5 minutes. What we can now do, we can get the whole distribution of x. So here's what that looks like. The dark line on the left is the prior. And you might notice that that looks a whole lot like the wait curve. In fact, the prior for x and the distribution of y are the same. And the reason is because of that uniform distribution, the uniform between 0 and 10. If it's been 6 minutes since the last train, I have to wait 4, and so on. It's symmetric. I'm kind of waving my hands at a lot of this, but I'll ask you to believe me that that's the right prior distribution for x. And now if I've seen 15 passengers, I do the update. The 15 passengers makes me think that it hasn't been very long since the last train. And so my posterior, oh, sorry, I said that wrong. It makes me think that it has been a while since the last train. And so my posterior belief for x is centered around 7.5 minutes, which was our guess a minute ago. If x is large, that makes me think that y is small. If it's been a while since the last train, there should be a short wait time. And we can do that. So here's the really difficult math behind all of this. Z is equal to x plus y. The time between trains is equal to the time since the last train plus the time that I wait until the next train. What I've got so far is I have figured out z, and I've figured out x. All I have to do now is infer y, and y is equal to z minus x. There's one slightly tricky part of this, which is they're not quite independent. I have to eliminate the impossible cases, but it's almost that straightforward. And here now is what that looks like. So again, the dark blue line is my prior for x. The medium line that's centered around 7 is my posterior belief about x. And the cyan line is my prediction for how long I think I'm going to have to wait. And in the example scenario that we were just running, that's relatively short. I think it's probably going to be about 2 minutes. I think it's unlikely to be more than 10. Okay. So the last piece of this is, yes, the decision that I have to make is whether to go upstairs and catch a train or not, and for that I need the probability that y exceeds 15 minutes. Because I've got 15 minutes to spare. If it's longer than that, I'm going to miss the commuter rail. I can now do this for each possible value of n, the number of passengers, and that's what this curve is. So the x-axis here is the number of passengers I observe when I arrive, and the y-axis is my probability of missing the commuter rail. And consistent with the intuition, if there's nobody on the platform, then I just missed the train, and it's going to be a while, so my chance of being late is medium-ish. Not actually that high, it's only 4%, that's okay. If there are a few people on the platform, then I know it's been a little while since the last train and I'm good. And as the number of passengers gets higher and higher, my nervousness about missing the commuter rail goes up and up. Okay? So that's what the outcome of that analysis looks like. Good. I wanted to show you this example for a couple of reasons. So one of them is, again, I observe these things in real life, and then like to do the Bayesian analysis to see if the Bayes thing is like the intuition. It usually is. It turns out that there's a good reason for that, which is that a lot of our heuristic thinking is Bayesian in nature. We do it approximately, and sometimes we do it in a way that's consistently wrong, but often we actually do pretty well at updating our beliefs when new data come in. Yes?
Is that where the crowd estimate works, where you can have a bunch of people guess the weight of the ox or whatever it is, and the individuals may vary wildly, but at the end it ends up being pretty accurate?
That's a good question. So the question is whether, is that the reason that crowdsourcing works? That if you ask a lot of people to guess the weight of the ox, any individual is not very good, but the average is better. Yes and no. So that's not necessarily a case where people are updating their beliefs on the basis of data. That's more an assumption about the way that people are wrong. If people are about equally likely to be too high and too low, then crowdsourcing works. But if everyone is biased in the same way, then you get no help. And so actually the example that I just gave is one where crowdsourcing would fail because we all have pretty much the same set of heuristics built into our brains. And so we're all going to be wrong in the same way. Let's see. So that was one reason I wanted to do this example. The other is it demonstrates what I think is a strength of the methods that I'm proposing for you, which is that they compose very well. The pieces are relatively simple, but when you solve a problem like this, you can assemble them. What I just did was kind of complicated, but it's one of the chapters that's in Think Bayes. So if after this tutorial you get a chance to work through the book, I think what you'll see is that all the pieces are relatively simple, but they allow you to take on a pretty complicated problem in a Lego-like way. You just put the pieces together. Each piece is simple, but they compose nicely. And then the last thing, I've said this a couple of times, but just to reiterate, a strength of the Bayesian analysis is that the result is in the form of a posterior probability distribution, which is exactly what you want for doing decision analysis. So if you're doing engineering or finance or other kinds of areas where you are making decisions under uncertainty, having the posterior probability distribution lets you, for example, minimize your expected cost or maximize your expected profit by looping through all the possibilities in the posterior distribution, computing the cost under each of those hypotheses, and then minimizing whatever you're trying to minimize. Okay. Good. All right. we are getting toward the end. I want to do two things. One of them is that you are supposed to do a survey to tell people how great this tutorial was. So let's do that. We'll take about 5 minutes, or as long as you like. You tell me when you're done. And then I have some reading suggestions for you. So we'll be back in about 5 minutes. Oh. Oh, yeah. Yep. That's funny. I actually had a pretty good, I did it for kind of a year and a half. And I think there were only 2 or 3 days where I arrived on the platform and something was obviously wrong. And there was only 1 day where I ended up walking. It's about 3 miles. Nick, I was thinking about your question, and there's
Like
mm-hmm.
then wouldn't it reflect like psycholinguistics using errors to using speech errors to analyze thought process, thinking of
Mm-hmm.
like that being an example of like a blind estimation being an example of the heuristic
Mm-hmm.
property of the decision making.
Mm-hmm.
Is what my head's telling me anyway.
Right.
Seems like there's a relationship, like almost.
Yeah. Well, so what you want is for the distribution of errors to be centered around 0.
Well, and if you're just blindly estimating a number
Yep.
without a bias, then it works, right? But then if you
Probably. I mean, it depends on how people are generating. But one of the ways that we fail to be good Bayesians is anchoring. That if I suggest a low value and then I show you data, you don't go as far as you should. And if I start high, you don't downgrade as much. And so those two people would end up separated when they should have converged. Is that the St. Pierre? Did you? Yep. Ah, very good. I've got my UFC sweatshirt with me. It's not for that particular fight, but. Did you go to the fights?
Yes.
Ah, very good. I've never actually. I've watched them all. You know, they're what are they at? 171 or 172? I've seen them all, but I haven't gone to any of them. Yeah. I bet that must go crazy. Do you think he's going to unretire? I think he wanted to lose that last fight. I think he wanted to. Well, I mean, I think he did lose the last fight. I don't want to say that around here. Ah, okay. Ah, okay. Oh, interesting. So you can infer how the judges are making their decisions? What do they give credit for? Yeah. Yeah. I will check that out because I'm very interested. Because they talk a lot about, some guy will get punched in the face 10 times and then he gets a takedown. How do you score that? Yeah. Is that enough time? Raise your hand if I should give you a little bit more time. Okay, let's get back to it. Good. Okay, a couple of suggestions for where you should go from here. One of them, obviously, think Bayes. I mentioned before, there's a free version of that that you can download, and you are certainly, if you want to have a hard copy of it in your life, you can do that. There are a bunch of case studies in that book. Some of them will look familiar. So we did the Euro problem, we did the SAT problem, and the red line problem. The Price is Right problem is if you are a contestant on the Price is Right and someone shows you the showcase and you have to guess the value of the showcase, you can update your prior based on what you see. So if you think it's a valuable set of prizes, you would go higher or lower. However, this is a case where the cost function is asymmetric, because if you are too low, that's good, you have a chance of winning. If you go over, then you lose. And so your strategy there is a little bit different. Again, this is an example where the posterior feeds into your decision-making process. The Boston Bruins problem is predicting the outcome of a hockey game. I predict that the Bruins will win. The paintball problem is the first example in the book that's two-dimensional. You might notice so far all of the examples are estimating a single quantity. The two-dimensional version is you are trying to figure out where your opponent is in a paintball match. And you do it if you enter the room, let's say there are a whole bunch of obstacles there, and you see paint spatters on the wall. You can infer where your opponent is based on that data, making certain assumptions about the randomness of your opponent's shooting ability. So that's a two-dimensional. The variability hypothesis is a comparison between two groups to see which one has a higher variance. In classical statistics, that's a hard-ish problem because the variance is more variable than the mean. And so this lets you quantify that. The kidney tumor problem is an interesting one, in part because it is a very pragmatic problem, and it's also an interesting example. The pragmatic part, this actually came from a patient who put a question onto a statistics forum, and he said, I've been diagnosed with a particular tumor. The tumor has a particular size, and I would like to know when this tumor is likely to have formed, because if the tumor formed while I was in military service, then my benefits would be different, depending on. And so this person was negotiating with the Veterans Benefit Association, or agency, or whatever it is. And so I was able to make a statistical argument about when it had formed based on the growth rates of tumors. The reason that's an interesting problem is that it's very easy to simulate the growth in a forward direction. In other words, if you tell me how old the tumor is, I can tell you the distribution of sizes. The Bayesian inference allows you to turn that around. Given the size, I can give you the distribution of ages. And that's exactly what the analysis is that I did. It's a general principle that anything you can simulate going forward, you can Bayesify and make the reverse inference. So it's often a very nice approach to problems like that that have a physical model behind them. The Geiger counter problem, I won't talk about that one for now. And then the last one is the unseen species problem. This one comes up in biology, especially ecological sampling. You go into an environment, it might be a nature preserve that has large animals, or often you have a beaker that's full of microbes, and you do some kind of DNA sequencing or RNA sequencing often, and you get a count of the different species that are there. But often there's a dominant species that makes up a large part of the population, and then a long tail of extremely rare species, some of which you've seen and some of which you have not. The unseen species is asking the question, how many other species do I think might be in this sample that have not yet shown up in my measurements? And that one's an interesting statistical problem. That's the last one in the book. If you are interested in the introductory statistics stuff, you also might want to work your way through ThinkStats, also available free. And now some of the other reading I mentioned. I mentioned Mackay's book. This is where I got the Euro problem. Really good stuff. He also talks about information theory. If you are not familiar with information theory, it's mind-bending stuff that will change the way you think. And I like Mackay's introduction to it is really good. So I recommend this book. It's available as a free PDF on his webpage. If you have my slides, that is actually a link to it, or just Google it and you'll find it. The other book I want to recommend is Cameron Davidson Pilon's book, which kind of doesn't have a title yet, or it has a couple of different titles. It is on GitHub. If you Google around for it, you will find it. It is all done in Python notebooks. So the book is a Python notebook. You can download that and execute some of his stuff. I recommend this book in particular because he takes a different approach. He uses the Monte Carlo, Markov chain Monte Carlo, MCMC, approach to doing Bayesian statistics, which is complementary in many ways to what I've presented. I think what I presented today is a good way to get started. I like it because it's conceptually very simple. The problem that you are going to run into if you start using this stuff is eventually a computational limit. We did one-dimensional things. In the book, I do two-dimensional things. If you get up to 3 and 4, you can do the computational approach that I took today. Beyond that, it's probably going to take too long to run. That's where the Monte Carlo stuff comes in. So his book kind of picks up from where mine leaves off. In fact, I stole the Price is Right problem from him. So I recommend that book. Oops, skipped one. There we go. A couple of books that are not free. Scientific Reasoning is the one that I couldn't remember the title of the other day. We talked earlier about using Bayesian inference as part of scientific inquiry. That's what that book is about. The notion there is that our beliefs about the world should be guided by Bayesian inference. Sivia's book is a nice source of problems. He takes the analytic approach, so it's not the computational version. If you get to that point where you want to really do the math, that's a good next stop. I stole the paintball problem from him. In his version, it's the lighthouse problem, but I turned it into the paintball problem. And Andrew Gelman's book is also very good, also the mathematical approach. So that is that. If you are working on a problem that's similar to some of the things that we did today, and you would like some help with it, I always am looking for interesting projects. I teach during the academic year, but I have time during summers, and I have a sabbatical coming up. So if you have need for lots of things, we can talk about that. I will take questions. I have a couple of slides that I could also tell you about. But yes, let's talk.
So, like, you alluded to some controversy, what's the controversial side of any of this?
Oh, good. What's the controversial part of it? Bayesian statistics have a funny history. I encourage you to look at it. There's a book called The Hypothesis That Would Not Die, which is the history of Bayesian statistics. And it is a century-long battle between two schools of thought about what statistics should be trying to do. And what's called frequentist statistics is in some ways the version that won for about 100 years. Bayesian statistics was considered unacceptably subjective. The controversial part is that everything that comes out of a Bayesian analysis is subjective, because if you and I start with different priors, we will end up with different posteriors. From a frequentist point of view, that is unacceptable, because science is supposed to be objective, and so frequentist methods are regarded by some people as being more objective. I don't buy that. I'm a Bayesian, so I will give you my version of the story, which is science is fundamentally objective. We're just stuck with that. There's no alternative. There's no statistical framework that magically makes the subjectivists go away. If you think you're being objective, you're kidding yourself. Subjectivity is actually an advantage of the Bayesian approach because you are confronted with the subjectiveness and forced to deal with it. So that's my really short take on the controversy and my response to the controversy. Other comments, questions? Am I really good at poker? Kind of yes and kind of no. So I actually use this informally to make decisions. So I'm doing, actually in poker, you are doing 2 levels of Bayesian updating. One of them is during a particular hand, you're updating your belief about your opponent's hand based on how they're betting. over a sequence of games, you are updating your belief about your opponents. So every time an opponent calls with a poor hand, you learn something from that. Every time they slow play you, you learn from that, and so on. So if you are doing those two updates at the same time, you will probably be an okay poker player. Nate Silver, he has a book called The Signal and the Noise, which I should have put that on my list. I also recommend that book. He talks very explicitly about how to use Bayesian thinking for poker playing. He did it. He played poker online using these principles and did well. What he found is that he actually didn't make enough money to pay for his time. So that's one way of doing the analysis is economically. I don't use this for gambling because I don't find gambling a compelling activity because it's a zero-sum game. If I make money by gambling, all I'm doing is taking that money away from somebody else. I like to participate in creative activities that are not zero-sum, where the world is a net better place because I spent my time on this. Other questions? Yes?
What if there are any other interesting enterprise applications for probability theory that, like some of the things that we learned today? Like I was thinking, like when you were talking about the, should I take a taxi or not? I was wondering, you know, like, well, I wonder how well that might work in algorithms to like every day on my phone it tells me, oh, it's 20 minutes to work, which is 8 minutes more than usual, and it does that by like measuring traffic and stuff like that.
Mm-hmm.
Wondering, do they use these sorts of algorithms for that, like traffic navigation?
Right. So the question is, what are the applications of this, broadly speaking? And the particular example is making a decision if you're stuck in traffic, should I take route A or route B, given data that I get from a live update? I see this stuff everywhere. Whenever I think about problems like that, I always think in terms of probability distributions and Bayesian updates. The world usually doesn't provide you with probability distributions. What you usually get point estimates when people report numbers to you. So yeah, I'm not sure I have a good answer other than what are the applications? Everything. Can you apply this to traffic? Yes, except that the inputs that you get are not the best kind of input because they're single point estimates rather than distributions. Yes?
I vaguely remember reading an article about how supermarkets determine pricing for products and how they've gone away from like a predictive algorithms to just basing their pricing totally on existing available data, and they just collect a huge number of variables. So it's like yellow Jello, the price goes up by $1 and they sell more of it, days after it rains or something like that. Are you seeing anything like a shift from going from let's say high frequency trading instead of trying to predict from here on out, just use the data that you have and not do that predictive model? Are you seeing,
Right.
is there
Yes, so I'll see if I can paraphrase the question. So what you're asking about is a shift away from model-based prediction and toward data-based prediction. And that's not specifically a Bayesian thing, but that is certainly a trend that I'm hearing about and seeing. Peter Norvig has an interesting paper about that, looking at examples similar to the supermarket example that you just gave, where you can build models and you can build these predictive frameworks, and ultimately you're just better off throwing data at the problem. I think that's interesting from a practical point of view. There are lots of examples like that, but there are also other examples where no amount of data helps you, and what you really do need to do is make smart modeling decisions. I made some arguments here about how to go about that kind of modeling. There's not a right answer to that. Those are complementary tools. You need both. Sometimes one of them wins, sometimes the other one wins. Yeah.
Would you mind if I gave you a specific problem? How you think of it as like a region?
Yes.
So where I work, one of the issues we have, so I work at a nonprofit that tries to get teams to volunteer. One of the problems we have is that we have a sign-up process where people can go and just click a button and they've signed up to commit to do an activity. Maybe it's donating clothes, maybe it's cleaning the park. The problem is on the other side, we ask them to report back if they've done it most people don't report back. About 5% of people that sign up actually tell us they've done the activity.
Mm-hmm.
And we've done some sampling and surveys, and we know more people do it than actually report back.
Yep.
The problem is that when we report the impact of it, we weren't honest, and we only report the actual people that have told us that they've done it, and the number of activities or whatever they've actually done.
Mm-hmm.
So if it's donating 10 items of food or cleaning up 3 pots.
Yep.
So we were always asked, well, how can you try to predict? Maybe we can try to predict how many people are actually reporting back.
Mm-hmm.
And we found out that one of our teams was telling sponsors that it's 5 times the business multiplying by 5. So we watched that fairly quickly. But
Yep.
is there an actual approach?
Good question. So again, let me try to paraphrase it. So you're observing a process where people say they're going to do something, and then they either do it or they don't, and then they either report back to you or they don't. And you only get to see the product of those two rates. You don't get to see either of the rates separately. And so you are trying to infer a hidden variable, which is the balance of those two. So in general, when you're trying to do that kind of inference, a Bayesian approach will work. Now the question is, how can you get some data that speaks to that one way or the other? And I'm struggling with that a little bit. The usual approach to this, if you have unreliable respondents, the usual approach is to try to make 2 different measurements that have 2 different error rates, and to use the difference in what you see in order to make the inference that you want. This is going a little off topic, but there's one really clever example of that where if you want people to give you a reliable answer to an embarrassing question, one of the ways to do it is to tell them to take their answer and then toss a coin and either flip the answer or don't, depending on the outcome of the coin, and tell you the result. And I think I haven't said that quite right, but there's a variation of that allows you to take their answers and infer the actual rate of positive response despite the fact that they have obfuscated their answers. And the nice thing is that nobody can infer, you couldn't say for any individual what their answer was, but you can say what the population average was. So that's an example of a kind of inference. It's not exactly what you're getting at, but it is a tricky problem. I believe that there is a Bayesian approach to it, but I would need to think about it more. Let me see how we're doing. We have just a couple more minutes. I'm happy to break if you have had enough. Good. All right. You guys have been great. I appreciate it very much. Thank you.